This is Mr. Craig, and I'm going to talk through working out this review worksheet for the test. I have a few examples on here. You can print this out and try it on your own and then see how well you did here. And what I have here for each box, I've got a designation set up here, and you can read the instructions there. In box number 1, I want you to calculate the number of valence electrons in the structure and then draw the correct Lewis structure. What I typically do is I'll start off with the number of valence electrons, so I know that xenon brings 8, plus each iodine brings 7, and there's 2 of those, so 14 plus 8 is 22, so we should have 22 total electrons in this structure. So we'll place xenon in the middle, and then iodine on the sides here, and wherever you want to put it, it's just fine. Keeping formal charges in mind, we want to make sure that the external atoms, which happen to be iodine, are group 7A, so they'll have a single bond to have a formal charge of 0. Then we'll put the remaining electrons on the iodine. Okay, so, and again, external atoms may only have 8 electrons. So right now in this structure I have a total of 16 valence electrons represented. For my calculation, we need 22, so that means that we need to place 6 more electrons on this. And again, we're going to place those extra electrons on the central atom. So I'll put 2 below the xenon, and again, I'll place 2 above the xenon. 2 pairs, I'm sorry. So now we've got our correct or best Lewis structure, and we go and do the formal charges. We already know the iodine's good to go, but you can always check that. But for the xenon, how many lone electrons? Well, we have 2, 4, 6, plus 1/2 shared, which is 1/2 of 4, which is 2. So there's 8 assigned electrons to the xenon, and their xenon brings 8 electrons, so the formal charge for this structure is good to go. Part B wants us to indicate the type of intramolecular forces. And again, intramolecular forces take place between atoms. So when we look at the type of force between the xenon and the iodine, xenon again has no electronegative value. So that means that these shared electrons between the xenon and the iodine has the most attraction or a higher electronegative value. So these are polar covalent bonds here. And again, what polar covalent means is unequal sharing, and the covalent simply means sharing. Part C says indicate the type of intermolecular force. So this is this a polar or nonpolar compound? We probably should have asked that question beforehand, which is part D. Looking at this shape, this is a linear shape with the 3 lone pairs around the central atom. So this is a nonpolar compound. So the type of intermolecular forces that we're going to have for this, there's only one choice: dispersion. All nonpolar compounds have dispersion forces. Since we already answered D, let's go right to E, and E asks for indicate the Vesper geometry. We already did that, linear. So it has a linear geometry. However, it has a potential of 5. In other words, if there were 3 more iodines that could be attached to the xenon, we'd have a trigonal bipyramidal shape. However, the AP exam only requires the molecular geometry, which is the shape that the atoms alone form. Part F, type of hybridization. Well, again, whatever the potential is, so number of external atoms plus lone pairs on the central atom, that is 2 external plus 3 lone pairs, so we should have 5 letters. So our hybridization is DSP3. So yes, this shape can exist because we can place electrons in the d orbitals. Xenon does have d orbitals. Part G, indicate the number of sigma bonds and pi bonds. Yeah, okay, so we have 2 single bonds between the xenon, and lone pairs don't count. So you'll have 2 sigma and 0 pi. And then H wants us to indicate the type of solid. So again, this is a nonpolar compound. We have nonmetal with nonmetal, so actually the polar and nonpolar doesn't matter. So we have 2 different nonmetals. So this, if this were forming a solid, it would be a molecular geometry. Okay. Let's go to the next example. SCl4, sulfur brings 6 electrons plus 7 for each chlorine for 4. 28 plus 6 is 34. Sulfur goes in the middle, put the 4 chlorines around. Again, formal charges, let's make sure the chlorines have their 8 electrons with single bonds because it's a group 7A compound. Right now I have 32 electrons, 4 times 8 is 32, so we have one more pair on the sulfur. The type of bonds that are taking place between the sulfur and the chlorines, they're different nonmetals, so there's unequal sharing. So we have polar covalent bonding. Is this a polar or nonpolar compound? So we can answer part C. This is a polar compound. This forms a seesaw shape. So we have a polar compound. Since we have a polar compound, we now have 3 choices. It's either ionic, dipole-dipole, or hydrogen bonding. Since there's no hydrogen, hydrogen bonding's out. Since there's no metal in the nonmetal, then ionic's out. So this has to be dipole-dipole bonding. Part E, what type of shape? We already said that. It's a seesaw. So seesaw shape. The geometry. So I have 4 external atoms plus 1 lone pair, which means I should have 5 letters, which is very similar to the shape above, which is DSP3. We have 1, 2, 3, 4 single bonds, so 4 sigma, and there's no double or triple, so 0 pi. And again, this is 2 different kinds of nonmetals, so a molecular solid. Okay. Looking at SO2. Sulfur brings 6 electrons, plus each oxygen brings 6, so we have 2, so a total of 18 electrons. Place sulfur in the middle. Since there's no charge on this, make sure the oxygens have double bonds. Make sure they get their 8 electrons first. In this case here, we have 16 electrons represented. Place the remaining on the sulfur. Sulfur may have more than 8. So this shape is okay. Type of bonds, so between the sulfur and the oxygen we have different nonmetals, and actually the oxygen has the higher electronegative value, so we have a polar covalent bond between the sulfur and the oxygen. This is a polar compound because of that lone pair of electrons. We actually have a bent shape. I'll just go right to that right now. We have a bent shape because it is a polar compound with that lone pair. So since there's the intermolecular force, no hydrogen, it's not a metal, so we have dipole-dipole again. The hybridization on this, 2 external atoms plus 1 lone pair, so we should have 3 letters. So we'll have sp2, again, 1 s, 2 p's. We have 2 double bonds, which means we have 2 sigma bonds and 2 pi bonds. Again, a double bond is a sigma with a pi. A triple bond is a sigma with 2 pi bonds. So in this case here we have 2 sigma and 2 pi. Again, this type of solid would be a molecular solid since we have 2 different kinds of nonmetals. Number 4, potassium nitride. Be sure that you're looking at your periodic table when doing these because every once in a while you'll get one of these thrown in. Potassium is a metal. And again, I'm going to write out the structure here first so that we can have the correct number of electrons. So potassium is a metal, and it has a +1 charge. Nitride is a nitrogen, which has a -3 charge. So that means we need 3 potassiums and 1 nitrogen, which means that we have 1 electron times 3 plus the 5. So we'll have a total of 8 electrons in this structure. Again, this is an ionic compound because we have a metal with a nonmetal. So what that means is each potassium is going to give away an electron. So we need to show brackets. Brackets represent 2 things. The first thing that it represents is that we have a different number of electrons from that which we started. Also, we put the charge on there to indicate how many electrons the element either gained or lost. So since each potassium lost 1 electron, and nitrogen only brought 5 electrons with it, we need 3 potassiums to make sure nitrogen gets its 8 electrons to have a -3 charge. So all these potassiums have +1 charges. This is an ionic compound. There is no Vesper. So no Vesper shapes involved here. The type of bonding between the compounds, between this ionic compound, between the atoms is ionic bonding. So the intramolecular forces happen to be ionic bonding. And again, all these nitrogens are attracted to a potassium. And again, this isn't the correct lattice or crystalline lattice structure that we're looking at, but the nitrogens, the negative part is attached to the positive part. Obviously, the nitrogen's a little bit bigger than the potassium, so the potassiums won't be next to each other, so to speak. The intermolecular forces are also ionic. Okay. This does form a polar compound, since it is ionic. And the hybridization, don't have any, since there's no sharing of electrons. Sigma and pi, we also don't have any, since there's no sharing of electrons. And the type of solid this would form is an ionic solid. So we like ionic compounds because we get to use that name quite a bit. All right, number 5. A couple more, I think. Iodite. Make sure that you know what the ITE represents. So iodate is IO3, so the ITE means 1 less oxygen. So we have IO2 with a -1 charge. So iodite is IO2 with a -1 charge. So iodine brings 7 electrons, plus oxygen has 6. So then that -1 means that we have an extra an extra electron. So we have 13 plus 7 is 20 total electrons in this compound. Go ahead and put iodine in the middle. Put your oxygens on the side. And let's be smart about this. We see that this has a -1 charge. So that means that one of these oxygens will be single bonded. Okay? So we place the remaining electrons around. And right now I have 16 electrons represented, which means I need to put 4 more on there. So I'm going to put a pair there and a pair there. All right, so doing formal charges, we already know the oxygens have, this oxygen has a formal charge of 0. This one has a -1. And if you don't understand why, do the formal charge calculations. For the iodine, well, let's see how many are assigned. So we have 4 lone electrons plus 1/2 shared, which is 2, 4, 6. So 4 plus 1/2 of 6 is 7. And then iodine brings 7 valence electrons. So this is a good structure. All right. What was that again? That was the type of intramolecular forces. So the forces between atoms, or again here and here, these are polar covalent. This is, even though it's a polyatomic, it does have a geometry, and this is a bent shape. So where's the name for the? So bent shape is up top. Hang on, yeah, bent. So this is a bent shape. It is a polar compound, not because it's ionic, because of the shape itself. So the type of intermolecular forces, you could say it's ionic, and it wouldn't be wrong, but I would dare say that most of us would say it's dipole-dipole. Now, it's interesting to argue this because with that -1 charge, there's no way this compound could exist without that extra electron. So if you said it was ionic, or if you said it was dipole-dipole, I would accept that. And the AP graders should also accept that as well. F, what does F represent? F represents the type of hybridization. We have 2 external atoms plus 2 lone pairs, so we should have 4 letters, so sp3, because it would be a tetrahedral shape if we had 4 oxygens. The number is sigma and pi. We have a single bond and a double bond, so that means we have 2 sigmas, and 1 double means we have 1 pi. This formed a molecular geometry. Technically, it would be ionic, but molecular is also accepted. Okay. So if you put ionic on there, I could live with that. I'll sleep tonight. Because again, that polyatomic cannot exist without a metal. So molecular or ionic is fine. All right, number 6. Ooh, that looks like fun. We've got chlorine, 2 oxygens. So let's go ahead. 7 plus 2 oxygens, 6 times 2, plus 2 bromines, which is 7 times 2. And there's also a charge of 1, so add another electron. Oh boy. So we've got 15 plus 13, so 38. Okay, so 38 electrons, put chlorine in the middle. Hopefully I did that right. Bromine, 2 oxygens. And there's a -1 charge, so that means that one of these oxygens has to be single bonded. Okay, so we'll go ahead and do that. Right now we have and then so right now we have 32, so we need, oh, did I do that right? Let's see, 12, hang on, let me do my math. 12 plus 14 plus 8, so 22, 34. 34 would be a much better number of electrons. All right, that makes me feel better. All right, so now, looking at the formal charges, and that's all -1, we have 2 lone pair, so two lone electrons plus 1 half shared, 1, 2, 3, 4, 5, so that's 10, half of 5, so good. So our numbers are good here. So we have our best Lewis structure there. And the bonds between, again, polar covalent. And again, this could be either dipole or ionic. Okay. This forms a seesaw shape. And it is polar, because we have that 1 lone pair of electrons, and that's not one of our exceptions. Sigma and pi, we have 4 sigma bonds. And we have 1 pi bond. And the type of hybridization would be 4 external plus 1 lone pair, so dsp3. I think I may have those boxes flip-flop. And again, this would form a molecular shape or ionic. Again, it would not exist without a metal. I know I went kind of quick through this. I apologize for the sloppy handwriting, but I hope this helped out.